All right, so the discussion we're going to have today is an intro into Chapter 7. Chapter 7 deals with light, right? Electromagnetic energy, electromagnetic spectrum. The first thing we talk about in the chapter when you read it is the nature of light. And there was a huge debate between physics and chemistry, which isn't really a debate, between whether or not it was basically light was a particle or a wave. There was arguments between Newton and this guy, this dude here, Huygens, basically just trying to figure out whether light was a particle or was light a wave. Evidence for light being a particle was the fact that it traveled in a vacuum, it reflected off objects, and it could exert force, especially like in the tail of comets. So that's an example of why light was thought to be a particle. We also came to the conclusion, some of the scientists did, I say we, but I wasn't around back then, that basically light consisted of waves. The evidence for that was it reflects like waves, light can refract and diffract like waves do, and it was possible to exhibit interference. We now know that basically it's called the duality of light, that light basically has both properties. It has some particle properties and it has some wave-like properties. Now when we talk about the wave issue or being able to label waves in chemistry, the first thing you have to understand is what is wavelength. The definition of wavelength is the distance for a wave to go through a complete cycle, and I'm going to show you a picture in a second. Amplitude is half the vertical distance from the top to the bottom of the wave, and then finally frequency is the number of cycles that pass a point each given second. So when you're talking about frequency, it's basically like when you compare these two up here, you have two sets. Think of frequency because we measure in hertz. Hertz is the same thing as s minus 1, it means per second. It's like a snapshot when you're taking a picture. So if you took a 1 second picture of this, you notice I have 1, 2, 3 full waves in this picture. So that's my frequency. Per 1 second, 3 waves are passing a given point. If I look on the bottom one, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So obviously the one on the bottom has a greater frequency. So here this is a greater frequency. Well, the relationship between wavelength and frequency is inverse. Notice how this one has a longer wavelength, this one has a shorter wavelength. So this one has a greater frequency. Frequency of this one is greater, frequency of this one is lower. So we know that wavelength and frequency are inverse related. Okay? Key things you need to know. You need to know amplitude is half the height, frequency is how many pass by. So amplitude would be half the height of a wave. Wavelength is from one point of a wave to another point, so crest to crest. This is considered the trough of the wave, right? So when we go through here, the other thing you're expected to know in chemistry is the 7 regions of the electromagnetic spectrum. We have radio waves, which have the largest wavelength, all the way to gamma rays, which have the shortest wavelength, but the highest frequency. So when we go, basically radio waves are huge. They're about the size of buildings compared when we talk in human-centric view. Whereas gamma rays are super small. Their wavelength is small. They're about the size of atomic nuclei, but they're very powerful. How do we remember all this? Easy way is red monkeys in Virginia use extra gum. Red monkeys in Virginia use extra gum. What does that mean? Radio comes first, then micro, infrared, visible light, which ultimately, remember when you think about visible light, you have to understand that that's Roy G. Biv. Those are the colors of visible light, starting with red, then orange, yellow, green, blue, indigo, and violet. And then we have UV. UV comes next on the list, X-ray, and gamma. Well, this is called the teeter-totter of light. That's what I call it. Over here, radio waves have the greatest wavelength. So if you just write red monkeys in Virginia use extra gum, and you know wavelength is on the left, radio waves are the highest. Think of a teeter-totter. Radio waves are the highest wavelength, and then they would have the lowest frequency and energy. If I go over here, gamma rays would have the highest frequency, highest energy, but the lowest wavelength. And then they could ask you to compare, like for example, they could ask you to compare orange to blue, orange color to blue color. Who has the greatest wavelength? Well, orange is closer to this side, so therefore orange would have the greatest wavelength. Blue would have the greatest frequency and the greatest energy. It makes it an easy way to have a fundamental understanding of the 7 regions of the electromagnetic spectrum and be able to identify wavelength and frequency. Now, here we have the band of visible light that represents Roy G. Biv. We already kind of talked about that. One of the first key equations you're supposed to know in chemistry is what I call the light equation. That is, lambda, which represents wavelength, times frequency, which is this little v symbol, equals c, which is the speed of light. The speed of light is 2.998 times 10 to the 8th. We're just going to round it off to 3.0 times 10 to the 8th meters per second. We use the light equation whenever we're given the magic words. The magic words are whenever frequency and wavelength are mentioned in the same problem, you know that you're going to use the light equation. That's basically your problem recognition. So if I look here, frequency, wavelength, I know in this case that I'm going to use the light equation. It's very easy to use because these two, when you multiply them together, are equal to a constant. So the speed of light is a constant. So when I go to set this up, I'm going to go 3.0 times 10 to the 8th meters per second goes there. What am I given? Well, I'm given wavelength. So basically I'm going to divide, since the speed of light is always going to be on top, I'm going to divide by what I'm given. You have to keep in mind units matter. That's how they sass up these problems. Wavelength always has to be in meters. Frequency always has to be in hertz, which means per second. So if I look right here, I notice I have nanometers. Now the conversion, I would have to basically convert that. So the first thing before I even go to my calculation is I'm going to do this. I'm going to convert. I'm going to take 8.21 nanometers, and I know this. I know that 10 to the 9th nanometers is equal to 1 meter. That's a conversion you need to know for the light equation. So what I would do is I would take my calculator and I would go 8.21 divided by 10 to the 9th, and I'm going to get 8.21 times 10 to the negative 9th. That would be my value for, and that's in meters. I've converted it into meters because meters is required and so is hertz. So then to solve the problem, I would go 3.0 times 10 to the 8th, and I'm going to divide that by 8.21 times 10 to the negative 9th, and I get 3.65 times 10 to the 16th. And in this case, frequency, I know my unit's always going to be in hertz. I'm good to go there. Sig figs are dictated by the number given in the problem. This has 3 sig figs, therefore your answer will have 3 sig figs. So the problems when you're using the light equation really center around making sure your units are correct. Here's another example. Calculate the frequency of visible light having a wavelength of 485 nanometers. Well, if I look, the first thing I notice is frequency and wavelength are mentioned in the problem. As soon as I know frequency and wavelength are mentioned in the problem, I know that basically lambda times frequency is going to be equal to c. So in this case, I'm going to take 3.00 times 10 to the 8th, fire truck there, meters per second goes, that's my constant. This is going to wavelength, basically it's going to be c divided by lambda will give me my frequency. I have to change this, so I have to do a conversion. So when I convert it, I'm going to go use a grid, 485 nanometers. I know that 10 to the 9th nanometers is equal to 1 meter. When I do the multiplication, I'm going to get 4.85 times 10 to the negative 7th meters. I have my meters on top, meters on the bottom. I'm going to get per second, which is what my unit is, which is basically hertz. So when I calculate this out, plug that in the calculator, I'm going to get 6.55 times 10 to the 14th, s minus 1, which is the exact same thing as hertz. So there's another example. We'll do one more example. CO2 absorbs light and the wavelength of 0.018 millimeters. Again, they're asking for frequency, so we know that it's going to be c divided by wavelength is going to get me frequency. In this case, this is millimeters. I have to change it from millimeters to meters. So what do I have to do? It's basically going to end up as being 10 to the negative third. So I just go 0.018 times 10 to the negative third. It's not exactly the correct scientific notation, but whatever, it's still converted. So what happens is my meters will cancel. I'll be left with s minus 1. Divide the two, and I get 1.7 times 10 to the 13th. Hertz is the same thing as s minus 1, which is per second. What is the wavelength of this? So wavelength, and this is frequency. So now it's the same idea, except this time I have lambda, and then I have frequency is equal to c. In this case, to get wavelength, I'm going to take the frequency and divide by the frequency. I have to check the units though. This is in megahertz. So basically, I have to change it using mega. Mega means 10 to the 6, right? So I'm going to go 90.7 megahertz, right? I need it in hertz. Well, 1 megahertz is equal to 10 to the 6th hertz. That's just a metric conversion. For this unit, you would have to know that. So ultimately, when you multiply this, you're going to end up with 90.7 times 10 to the 6 basically is what you're going to get. The value of the constant is 3.0 times 10 to the 8th meters per second. This is s minus 1, so they cancel. So I'm going to basically be spitting this out in meters. Your ultimate answer when you do the calculations is you're going to get 3.31 meters. So key things you want to remember, you have to know the 7 parts of the electromagnetic spectrum. Red monkeys in Virginia use extra gum. Know the frequency and wavelength. And the first equation out of this chapter is the light equation, which is basically lambda, which is frequency, or lambda, which is wavelength, times v, which is frequency, is going to be equal to c, which is the speed of light. So whenever you go to solve one of these problems, you're just dropping whatever variable they give you, making sure the units are correct, and then solve. Should be a piece of cake. This is an easy equation. I will see you tomorrow. Have a good night.